Bismillahirrahmanirrahim. Electrical network analysis. In the second portion, we will discuss a new chapter, the Laplace transformation. Okay. So in Laplace transformation, we are transforming a function from time domain to Laplace domain, Laplacian domain, and it is represented by a t. So, for example, this is t, and when we apply Laplace, so it will be converted to S domain. And if you want to resolve it and you want to back it in the time domain, so you have to apply the inverse Laplace transformation and you will get your function back in time domain. So that's transformation just for the sake of our calculation makes easy. The transformation will makes our calculation easy, so that is why we are using this transformation method. So, and at the end, we are applying the inverse Laplace to get back our function in time domain. Okay, so, and similar is the case with the Fourier transformation. In the Fourier transformation, we have the frequency domain, and we can also call it a omega domain. Okay, so if let's suppose we have t, so we will apply a Fourier transform. The Laplace transformation is represented in most of the books by this symbol, the stylish L, and the Fourier transformation is represented by the stylish F. Okay, these are represented by the Oppenheim signal system by Oppenheim. Okay, so there are many transformation methods, that is the Laplace transformation, the Fourier transformation, the Z transformation, etc., used to perform the signal or the function from one domain to some another domain in order to make our analysis easy. In Laplace transformation, we will transform the signal from time domain to S domain, and the S domain will be S plane. So in S plane, we have the real value will be represented by the A, imaginary by the G omega. Okay, so that is the S plane. So if limits approaches from minus infinity to plus infinity, so it will be a bilateral, but usually we use the limits from minus infinity to 0 or from 0 to infinity means unilateral plane. So let's suppose we have a function f of t. So by definition, Laplace of f of t is equal to from minus infinity to infinity f of t e raised to the power minus st dt. If you want to convert the functions from S domain to time domain, then we will use the inverse Laplace transformation, that is L inverse of f of s is equal to 1 over 2 pi j from minus infinity to infinity f of s e raised to the power st. Here we have the e raised to the power minus st, and now we have the e raised to the power st. Here we have the function f of t, and now f of s ds. Okay, so there are a few standard functions. Okay, so let's start with the unit step function. The unit step function is represented by u of t, unit step function. Okay, it is mostly used for the filtration purpose. For example, if we have any function, for example this, okay, sorry, this is the negative portion from minus infinity to 0, and this 0 from 0 to infinity portion. So if you want to get the positive portion of this signal, you want to filter out this negative portion, and you want to get only the positive. So you can do it easily by multiplying this with the unit step function. According to the definition, unit step function is from 0 to infinity, means for t greater than 0 its value is 1, maybe greater than 1. Okay, it depends, okay, on the coefficient. So for the standard unit step function we have only 1, because if you we don't want to disturb the magnitude of the function for which we are getting the filtered filter version. Okay, so we only filter out this region and want to get the positive without disturbing the amplitude. Okay, so for that purpose u of t must be equal to 140 greater than 0. Okay, and 40 less than 0 it is 0. And for the unit step function we have the flipped version as well, that is called u of minus t, but it's not uh, in your course. For the time being we will discuss it in signal and system. So for the time being we will focus only to u of t. Okay, so for t greater than 0 equal to and greater than 0 its value is 1. Okay, so by multiplying it with this you will get the solution of this. Okay, in this portion only, that is because of this u of t. So it can be used for the purpose of filtration. Okay, so and the another standard function is unit impulse function, represented by the sigma. Okay, okay, sigma of t is equal to, for t is equal to 0 its value is 1, and its value is 0 otherwise, means for t greater than 0 it is also 0, and for t less than 0 it is also 0. Its value is 1 only at t is equal to 0. Okay, here we have unit step function. Okay, and unit impulse function. Here is 0 0. So if you want to get this can be also used for filtration purposes. If you want to get the magnitude for a single impulse. Okay, so you, for example, if you want to this, so there may be a shifted version of this. For example, u of t plus 1, u of t minus 1. Similar, uh, there may be a shifted version u of t plus 2 and u of t minus 1, for example. But these are not uh, the part of the course in electrical network analysis. So we don't need to discuss it. So we will discuss only the standard version, that is u of t and sigma of t only, not the shifted version. Okay, so for example, we have u of t and we want to apply the Fourier transformation. Okay, so according to the definition, Laplace of f of t is equal to minus infinity to plus infinity u of t e raised to the power minus t. For any function we have to multiply e raised to the power minus st. According to the definition, u of t is minus, from minus infinity to 0 it is 0, and from 0 to infinity it is 1. So this whole portion will be 0, because 0 multiplied by this is equal to 0. So we will left with this portion only. Okay, so applying the integration, it is for minus st divided by minus s limits, putting the value, the limits infinity, it is for minus infinity, it is for 0. So we will get, okay, now we want to get the a definite value, means some defined value, not the undefined. So we have to avoid the undefined case. Okay, so for this purpose, 1 over e is for infinity, and e is for infinity is infinity, and any 1 over infinity is equal to 0. So that portion will be equal to 0. We will left with minus 1 only. So minus into minus plus, so the answer of u of t, the Laplace of u of t is 1 over s. So we have to remember this, because for some higher terms, for example in the case of the circuits and anything higher function, or in the case of the inverse Laplace transformation, if you get 1 over s, so it means the inverse of 1 over s would be u of t. Okay, now for example we have the exponential function, exponentially decaying function e raised to the power minus at. So Laplace of e raised to the power minus at. Okay, e raised to the power minus at into e raised to the power minus st. Okay, so here it is given that the t is greater than 0. So we will consider only the unilateral plane from for t greater than 0 means here we have from 0 to infinity. So the bases are same, their power will be added e to the power minus taking okay minus um, a plus s taking minus common. Okay, minus will be common. Okay, so applying the integration minus a plus s. Okay, so putting the values e to the power minus infinity is for 0. We have discussed it in the previous slide that e to the power minus infinity is equal to 0. E to the power anything power 0 is equal to 1. So minus plus 1 over a plus s. So you have to also remember that the plus of e to the power minus at is this. Remember, if we have minus over here, so the answer is plus. If we have plus over here, so here the answer will be 1 over a minus s then. Okay. Now, if we have t, the ramp function. Okay. So, for example, Laplace of t according to the definition, and t is greater than 0. So, we are only considering the t is greater than 0 means unilateral plane from 0 to infinity t dot e to the power minus st. Now, as we have the integration, so we have to apply the integration by parts. First into integration of second minus integral differential of first integration of second. So as you know that in integration by parts, you have to consider that function as first, which is going to decay by applying the derivative. Okay, so that is necessary. So if you take it as 2 and that is 1, so it will goes high and high and the answer will be endless. So take care of this. Okay. After integration by parts, putting the limits 0 to infinity. Okay, so we will get 1 over s square. So then the Laplace of t is 1 over s square. Okay, now we will apply the Laplace transformation to the circuits. Okay, RC circuit, RL circuit, and then we will have different cases for the RL and RC circuit and RLC circuit as well. Okay, so we will discuss different cases in the next lecture, and somehow we have touched these cases in AC transients. Okay, so more or less these will be same. Okay, so d by dt, Laplace of d by dt, remember Laplace of d by dt is s. Okay, so if we have the one power, so d power 1 divided by dt power 1. Okay, so Laplace is s power 1. Now if we have double in derivative, okay, so d square over dt square, so Laplace will be s square. For triple derivative, the Laplace will be s cube. So from this we can say that d n derivative dn over dtn, Laplace will be s raised to the power n. Okay, now transfer function. What is the transfer function? Transfer function is the Laplace of the output variable over the Laplace of the input variable. Okay, so output and input may be changed from circuit to circuit. It depends upon the given values. Okay, so the Laplace of the output quantity over the Laplace of the input quantity. La- Laplace version of output and input version is necessary. Okay, output or input is not the transfer function. Laplace of the output divided by Laplace of the input is the transfer function. So uh, let's apply this to RL circuit. First, the given is R is equal to 4, L is equal to 0.5. Okay, now they told us to find the transfer function for this function where output quantity is I of S, means this current is this is a series, so in series the current through all the elements are the loads is same. So if is our output term, and v of s v of t. Okay, this supply, this is our input. Okay, so we have to find is over vs. So the first step is kvl. Okay, v of t is equal to vr plus vl. Voltage drop across the resistor, voltage drop across the inductor. So in time domain, first of all, vt is equal to I of t r plus L di by dt. Now applying the Laplace transformation, v of s. Okay, t will be substituted with s. Okay, and remember, okay, small I will be written as capital I. So capital I of s r plus L, the d by dt, d by dt of Laplace is s. So L s I of s. Okay, so taking I common, v of s is equal to I of s r plus sl. Now as we need I over v, so I over v, so by cross multiplication we will get, first of all, dividing I on both sides. Okay, and then taking the and invert it. Okay, and after the inversion we will get I over v is equal to 1 over r plus sl. Putting the values, r is 4, s and l is 0.5. Okay, now if you want to get h of t, means in time domain, so you have to apply the inverse Laplace. Inverse Laplace is equal to inverse Laplace of 1 over 4 plus 0.5 s. Okay, now remember that for inverse Laplace, okay, so you have to make it 1. Okay, coefficient of the higher term of s should be 1. In this case, the higher term of the function is s power 1. In RLC circuit, where we have the two energy elements, so the higher term will be s square. So then the coefficient of s square must be 1. But in this case, RL circuit or RC circuit, the higher term is s, so the coefficient of the s must be 1. Okay, so for this purpose, we have to divide this thing with on in numerator and denominator. So dividing zero point 0.5 over here and dividing zero point 0.5 over here. Okay, now solve the bracket. So we will get 4 over zero point 0.5 plus 0.5 for 0.5, 0.5 will be cancelled out. So we will, the 4 over zero point 0.5 is 8. So we will left with 2 divided by, we will get 2 divided by 8 plus s. Now the coefficient of s is 1. Okay, so that is because we are actually matching the situation with this e raised to the power minus, remember, I've told you in the previous slides that you have to remember that the Laplace transformation of e raised to the power minus at is equal to what, 1 over s plus a. Okay, here we have the minus, so here the answer will be s plus a. If we have the plus, then we will the minus over here. So now we have the plus, so and here the a is equal to 8. Okay, so h of t is equal to 2 e to the power minus 80, means 80. A is 8, so e to the power 80. So that is h of t. Okay, so we will discuss some more circuits, RLC circuits with different input and output variable, and RLC circuit as well, and the different cases, the undamped, the underdamped, the overdamped, and critical damped, with different values in our next class. So that is all for the moment. Thank you.